Okay, so a confidence interval is also known as an estimate uh, estimate interval. We don't know the true population mean. We don't know the true population proportion. We don't know the true population standard deviation. And when we don't know these things, we don't know them in general. We have to estimate them. And a confidence interval is just an estimate with a kind of a worst case and a best case scenario, right? Hopefully you read that in the book. A lot of people don't really understand hypothesis testing and confidence intervals. Very smart people, editors of journals. To this day, I've seen things that shock me in terms of misunderstanding what a confidence interval is or hypothesis testing is. But a 95% confidence interval, that 95% doesn't represent the probability that the mean will be in between two numbers. That's not the probability that the population mean, which we cannot know, will be between two numbers. That's not what it is. What a confidence interval is it assumes that you can do this experiment 1,000 times, for example, or 10,000 times, or 100,000 times. In reality, you're probably gonna do it once. In theory, you could do it, say, 1,000 times. All the 95% confidence interval says is that if we do an experiment 1,000 times, 95% of the time, we expect to contain the true population parameter. That means 50% of the time, or 5% of the time, that we expect the intervals that we compute to not contain the population mean, right? The probability that the sample mean is in your confidence interval is 100%, because the sample mean is at the center of a confidence interval, right? That sample mean can be way off or it can be right on the money. Most of the time, it's going to be around the truth. If we sample, if we have a random sample and that sample is representative of what we're trying to estimate, right? So most of the time, we're going to be probably around the true population proportion or the true population mean. But, you know, Bill Gates, the probability of Bill Gates being in a sample is equal to the probability of me being in the sample, right? There's 330 million Americans. One happens to be Bill Gates and one happens to be me. Now, I'm more average than Bill Gates in terms of wealth and income, right? He's an outlier when it comes to wealth and income, right? But he has the same probability of being in the sample as I do, right? So there are times when a random sample isn't representative. And in those times, your population parameter is not going to be estimated well by a confidence interval. The confidence interval will be way off, right? So what this does is it gives us a good idea of a best case and a worst case scenario, right? That's what an interval is. It's two numbers, right? There's the high number and the low number. And we're hoping that the truth is in between those two numbers, right? And all it is hope, right? All it is hope. Okay, so at the bottom of this table, we have a list of current employees and former employees. Former employees, the variable quit equals 1. For current employees, the variable quit is equal to 0. 0 is no, I did not quit. 1 means yes, I did quit, right? And then it has how much time they spent traveling for the company, right? So there's two variables here. There's the dummy variable quit, and then there's the amount of time they spent traveling for the company, right? So we're going to copy these data, and we want the names of the columns to be employee, person on the road, and quit. We want those names to appear in cells A1 to C1, right? So I'm just going to copy this entire table and put it in Excel. You want to make sure that you copy everything in the table and then something outside the table, right? So I'm copying the table and the letter S in this button down here. I'm going to paste it right here. Now I chose paste special, right? Or I chose match destination formatting. And that, again, as I've said over and over and over, that strips out all the HTML junk from the website, right? That will paste in just the text, right? The text. Okay. Okay, so yeah, the last row are in 150 and C150, right? And I can delete the S here. All right, cool. Okay, so we want to compute a 95% confidence interval for the proportion of employees who quit, right? I'm going to center this. Now what I'm going to do is I'm going to name these ones and zeros. I'm going to name these ones and zeros quit. Okay, so I got all the ones and zeros highlighted, right? I'm going to name it quit. I'm going to write the word quit right up here. That box that's right above the letters A and B, right? For column, I'm going to write quit. Then I'm going to hit enter. Make sure that I'm going to type equal quit. When I type equal quit, notice that all the numbers, ones and zeros, are highlighted. See that? Everybody got that? All right. If you don't say anything, I'll assume that you did. And I'm going to delete it. Now I'm going to copy this table. I'm going to copy this table, the components of this table. I'm going to copy everything in the table, plus I'm going to grab something outside the table, right? Actually, what I'm going to do is I'm going to get the instruction right here. I'm going to copy that all the way down to conference interval. Then in E1, I'm going to paste match destination formatting. Now let me widen this up because I don't need to go back to my open math for a while, right? Okay. I'm going to call the lower limit LL. I'm going to call the upper limit UL. Okay? Then I'm going to move my hints. My answers. I'm going to get rid of the word hints. Okay. You guys get that? Let me know when you get that. Also, I'm going to merge this cell and this cell together, and then I'm going to word wrap. I'm going to left justify. Okay. Let me know when you get to this pot.
How did you merge E and F?
Okay, so we got it formatted really nicely here, right? Now I'm going to click on the cell, the equal average cell, and I'm going to double click on it, and I'm going to go to the front of it right here. There's probably a space in front of the equal sign, right? So the first thing you want to do is you want to get rid of that space in front of the equal sign, right? Now I want the proportion of employees who quit, right? If you look at, hang on, I'll resume recording. Now we want to take the average of quit, right? Why do we want to take the average? What does average do? It adds up the values, ones and zeros. So if we're adding ones and zeros, what is it counting? What's the counting?
Basically, the percentage of how many people quit
Yeah.
overall.
So first, the step one of an average is to sum everything, right? It's to sum everything. So when you sum a dummy variable, ones and zeros, you're counting yeses, right? And then you divide by the total number of employees in the variable, right? And that gives you the proportion like what Craig said, right? So first, the average sums, in this case, it counts yeses, right? Because ones represent yes and zeros represent no, right? So the average sums that or counts yeses, and then it creates the relative frequency, the relative freq, right? So the sum gets the frequency of quit, and then averaging divides that count, that sum, to give you a relative frequency, which is called a proportion, right? All we have to do is type quit, right? Yeah, all we have to do is type quit. It's going to average the word quit, right? Quit is the object that is highlighted by the blue box, right? So we're going to add the ones and zeros, and then it looks like we're going to divide by 149, right? Because there's 149 employees here. All right. And then hit enter. And in my model, I have 43.62% of employees who quit. That's a high number, right? That's a high number. All right, now we want the number of employees, right? We already know it's 149. But if we have a data set that's millions and millions of things long, we want to count it by hand, right? So make sure there's no space in front of the equal count A. And then all you have to do is type quit. It should be 149, right? 149. You guys got it? We're good? Okay, the next thing, you can show mathematically that the variance, you can show that the variance of this dummy variable quit, the variance of the quit dummy variable is your P times 1 minus P. You can show that that's the variance mathematically in a proof, in a mathematical proof, right? P being the proportion of employees who quit, right? So numerically, what this is, it's P proportion times 1 minus proportion, right? That's the variance. You can show that mathematically that that's the variance, right? You can do a shortcut in Excel. Notice I have var.p here, not .s. When we're talking about a proportion, when we're talking about a binomial variable, we're using basically the normal distribution to estimate. We're using the normal distribution to estimate this binomial distribution, right? So even though this is a sample of data, using var.p gives us the same answer as this over here. So I got var.p, I'm going to type quit. This is equal again to proportion of employees who quit minus one minus the proportion of employees who quit, right? See that? They're the same thing. So you only use var.p when you have a dummy variable in a sample. Okay. Otherwise, you use var.s, right? Yeah, and I can show that to you mathematically in a PowerPoint if you want. I did this years ago, but you can push the I believe button or wait until after the session's over with, and I can walk you through the proof, right? Now the standard error of the proportion, is just like it is for a confidence, for the standard error of the proportion is identical to the standard error of the mean. And you can calculate it this way. You can take variance of this dummy variable quit, and you can divide it by your sample size. Yep. Now this ratio is actually the estimated variance of P bar, right? This ratio that we got here, F4 divided by F3, this ratio is actually the estimated error or the estimated variance of P bar. What is P bar? This is P bar. Why do I call it P bar? Because it's a sample proportion, right? And if I do this experiment 1,000 times, and each time I do it, I have 149 employees. Each time I do it, I have 149 unique employees or different employees. I'm going to get a different P bar, a different proportion of employees who quit. P bar is a sample proportion, right? So if now, Craig, what is your P bar? What is your proportion of employees who quit?
If we round to the nearest three decimals, I've got 0.436,
What about 4 decimals?
same as yours.
0.43624.
Whoops. Yes.
Huh, that's weird. Maybe I don't have it set up, but Quagmire, do you have the same 0.43624?
Yes,
You have the same? Huh.
but my numbers are different than yours. Like the percent on the road, those numbers are different. I just think that they're all so close together, like the total, that we're
Okay.
gonna get similar answers.
Oh, so these are different for you, but you have the same exact proportion here?
Yeah, not the further out that we get, but the up until the 43624, yeah, it's the same.
Who
Okay,
knows? We
that's
may get different answers later on.
yeah. Yeah, that's kind of weird because it's supposed to vary from student to student. But that happens in random sampling, right? You can
Mhm.
randomly sample this. You can, it's possible. The probability is probably close to 0. But you could possibly in a sample, a random sample, randomly sample the same 149 employees, right? That is possible. It's not likely, but it's possible. But the thing that I have in this box here, that thing right there, that should vary from sample to sample, right? It should vary from sample to sample. And so this right here would be the variance of those proportions. It'd be the estimated variance of those proportions. Now to convert it to the standard deviation, we put SQRT in front of it. Now we're taking the square root of that. We're taking the square root of that. Taking the square root of that ratio, right? When we take the square root of that ratio, the result is the standard deviation of the sample proportions. So from sample to sample, this numerical value is going to vary from sample to sample, right? And so this is that standard deviation of these P bars. So if we do this experiment 1,000 times, we're going to get 1,000 different values for the P bar, right? And this will be an estimate of that standard deviation, right? Now there's another name for standard deviation of the proportion. There's a different name for standard deviation of the proportions, the sample proportion. It's called the standard error of the proportion. So when we take the square root of that ratio, we get the standard error of the proportion, also known as the standard deviation of the sample proportions. Okay. And let's just make sure we get the answers correct. 3 decimal places, right? Okay, so I'm going to put in 0.436. I'm going to put in 149. I'm going to change that to counting number, right? You can't have a decimal there, right? I mean, you can, but I'm going to leave it as 149. The variance of the dummy variable, quit, is 0.246. The standard error of the proportion or the standard deviation of the sample portions, 0.041. And then my alpha divided by 2, is, this is my confidence level, right? My confidence level. So the confidence is the middle, in this case, the middle 95%, right? So this is 1 minus alpha, right? So the middle 95% is near the, it's at the well, I'll just pull up stats distributions. We're using normal approximation here. So the middle 95%, we're talking about this right here, this purple area. We have this 95% in here, right? The lower critical value is negative 1.96. The upper critical value is positive 1.96, right? The alpha level is the area in the tails, right? If the area in the tails is 0.05, right? If the area in the tails is 0.05, that means the area inside the tails is 0.95, right? So the area in the tails is 0.05. But I want to split that area into 2, right? I want to split that area in 2. So if I do a left tail here, you see that? 0.025 corresponds to a lower critical value of negative 1.96. Y'all see that? So my area in the hump is 95%. The area in the lower tail and the area in the upper tail is 0.05. I got to divide that area in the tail. Alpha is the area in the tail. I can divide that by 2 and I get 0.025, right? That's why this is, yeah. So this right here is the area in the tail. This right here is this is the area in the hump, right? That's the area in the hump inside the tails. This difference is the area in the tails. And you divide that by 2, you get the area in one of the tails, right? A confidence interval has 2 tails, 2 numbers, right? So you have to divide the alpha by 2. So this ends up being 0.025. Okay, and I can use norm .s.inverse to find this critical value, right? And all I got to do is click on the probability value up here, right? I use norm.s.inverse because the input to this formula is a probability value. And alpha divided by 2 is a probability value. It's the area under the curve, right? On the left side of the distribution. And the critical value is negative 1.96, right? Oh, by the way, why did it actually is a negative 1.96, right? I want to get rid of the negative symbol. I mean, I can do this. I can just type this as positive here, right? I can do equal absolute and then click right here. So I have a plus or minus 1.96, right? I have a plus or minus 1.96, plus or minus 1.96. Okay, and that goes back to my distribution here, right? If I have a two-tailed test, I got negative 1.96 that corresponds to this lower tail probability. I have 1.96 that corresponds to this upper tail probability. The probability of being between negative 1.96 and 1.96 is 0.95, right? Okay, so the probability of being in this white area here, that probability is 0.025. This white area here is 0.025. That corresponds to 1.96, and this corresponds to 1.96. If I'm looking at the area in between, 0.95, I get 2 values, negative 1.96 and 1.96, right? Okay, now the margin of error, what I'm gonna do is I'm gonna do it with 1 critical value. I can either use ABS or I can just make it negative. I can put a negative sign in front of it. Because 2 negatives is a positive, right? Margin of error is just that critical value times my standard error. And it's just the critical value times the standard error. And my margin of error is 3 decimal places is 0.080. My critical value is 1.960. And my margin of error is 0.080, right? And then the confidence interval, again, the center of the distribution is proportion of employees who quit. We're going to do equal P bar. That's our P bar, right? In this particular sample. We're going to subtract off our margin of error, right? And then we're going to do the upper limit. Upper limit is the margin of the P bar plus the margin of error. So it's our proportion 436 plus or minus 0.080. Okay. So at best, 51.6% of our employees quit. At worst, maybe I should rephrase it, right? At worst, 51.6% of our employees quit. At best, only 35.7% of our employees quit, right?
Show the formulas to those things.
Yeah.
0.357.
It's just the portion of employees who quit minus the margin of error, right?
All right.
And then this one over here is proportion of employees who quit plus the margin of error, right? So if we had a null hypothesis, of this, we'd use a confidence interval to test it, right? The null hypothesis was our mean, our proportion equals 0.5. If that was our null hypothesis, we could use a confidence interval to do what? 0.5 is in between these two, right? 0.5 is in between these two. So we'd have evidence in support of the null hypothesis. So we would not reject the null, right? So you can use a confidence interval to do a two-tailed test, right? Two-tailed test. Only in the hypothesis testing, when you calculate the variance, you don't calculate the variance from that. In hypothesis testing, you calculate the variance from what we believe the hypothesis, what we believe the proportion to be. So if this were a hypothesis test, our standard error would be, our variance of D would be this instead.
Hey, how did you calculate the margin of error again?
Margin of error is just the standard error divided by or times the critical value. It's just the standard error times the critical value. If we're doing the hypothesis test, our variance D would be slightly different. But that doesn't really affect our standard error, right? Our standard error is basically the same to 3 decimal places. So a lot of times, especially under large samples, lot of times the program that you're using will just use the variance of the dummy variable to compute the. So I'm just going to go ahead and delete that. I'm just showing you that you can use a confidence interval to not reject this null hypothesis if you think the quit rate is 50%, right? If your boss says, we think the quit rate is 50%, you could test that, that hypothesis with a confidence interval, okay? All right, so we have a best case scenario, 35.7% of our employees are quitting, right? So we want to dig a little deeper and figure out why, right? So down here, we're going to compute the 95% confidence interval for the percent of time spent on the road for those who did not quit. So for those who did not quit, right? So what I want to do here is I want to highlight this first row. See that with my mouse? I want to highlight this, and then I'm going to press Control Shift and down arrow. Highlight all of the information, right? See that? I got all the information highlighted here. Okay. Then I want to right click. Now, notice I started with the number under quit, right? I'm starting here under the word quit. See, I got this white box here. Everything else is gray, right? Why do I want to do that? I'm going to show you that in a second. I'm highlighting everything below the words employee, percent on the road, and quit. All the numbers. All the way down to the bottom, right? And when I highlight all this information, you should see this number below quit should be white and everything else should be gray. Why? Because I want to sort on quit. So I'm going to right click on the shaded region. I'm going to find sort. Then I'm going to sort smallest to largest. And notice what happens here. All the zeros are placed on top, right? All the zeros are on top. Notice my employee number has been switched, right? It no longer goes from 1 to 2 to 3 to 4, right? And then we get down here for the ones, right? For the ones under quit, now I got 1, 3, 5, 6, 7, right? You see that? You want to highlight all 3 columns and sort all 3 together. If you don't, you're going to get messed up numbers. Okay. Now I'm going to name this. I'm going to name this variable of these. I'm going to name it where quit is 0. Where quit is 0. See that? I'm only highlighting the person on the road when quit is 0. You see it? I'm only highlighting percent on the road for quit equals 0. Okay. I'm going to name that percent on the road not. You can call it whatever you want. We'll call it percent on the road, POR, NQ. We call it POR, NQ. But this, all capital letters. Percent on road, not quit. But PO and Q. POR and Q is porn Q, right? I'm going to stay away from that. I'm going to call it PON-Q. Percent on, not quit. Okay. I'm going to name those. Okay. Any questions on that? Any problems with sorting them together? You can use your mouse to do it. I just find it faster to use hotkeys, right? So in review, you want to sort on the variable quit, right? You want to sort on the variable quit. You do that by highlighting from just below the word quit all the way to the bottom. Then you right click, sort smallest to largest, right? And then you want to name the values under percent on the road where quit is 0. Right? So I highlight this all the way down to where quit is 0. And then none of these down here are highlighted, right? And then we named that, we named it PONQ. Point on, not quit, just to be brief. Okay. Now I'm going to copy this. I'm going to copy the instruction all the way down to confidence interval. I'm going to copy that. I'm going to paste it right here. I'm going to choose match destination formatting. And then I'm going to merge these 3 cells. I'm going to merge those 3 cells. I'm going to word wrap, left justify, and then make the row taller. Okay. Then I'm gonna get rid of the word answer and hence. I'm gonna move my hints to column F. I'm gonna change this to LL. I'm gonna change this to upper limit. Okay. I'm gonna make this bold. Okay. You guys get it? So I kind of made it look just like that, right? I'm going to center this. And I'll center this later, right? You guys get it? Quagmire, you good?
Yes.
Craig, you good?
Yeah,
All right. Can I move on?
let's do it.
All right. So now I got equal average here, right? What am I going to type? Percent on, there it is right there, right? PO. Got FX, that means function. But this table here with 2 blue row cells, that means this is a name of a group of cells, right? So I'm gonna double click on that. And I'm gonna verify that my percent on the road associated with quit equals 0 are all highlighted. And that's the case, right? And then I'm gonna hit enter. My average, my mean percent on the road for those who did not quit is 34.407. I'm going to put that over here to see if I got it right. And it looks like I did, right? Whoops. Now I want to do the count, right? I want to do the count of percent on the road, not quit. Okay. Percent on the road, not quit. Again, I want to verify that only the percent of the road associated with quit equals 0 is highlighted. And that is the case, right? I'm going to hit enter. And I get 84, right? Okay. Now I want to do variance percent on the road, right? I'm going to take the variance of only 84 things, right? And I have var.s here, right? You only use var.p if you have a dummy variable, ones and zeros. Otherwise, you use var.s, right? And again, I'm going to use PONQ for percent on the road, not quit. Yep. Again, I'm going to verify my blue box is taking the variance of percent on the road associated with the word quit equals 0, right? Hit enter. Reduce number of decimal places to 3. I'm going to copy that and I'm going to put 84 into here. Right? Put 84 into there. I'm going to put my variance right there. You guys got it? Good? You getting the green check marks?
Yes.
All right. Now my standard error, it's just, again, the standard error. Let's do the variance of the sample means first. This is the variance of the observations that are the 84 observations in column B, right? That's the variance of the observations. When I divide that by the count, I get the variance of the sample means, right? And I say sample means with plural because I can replicate this experiment as many times as I want, right? So every time I do a sample of 84 employees who quit or who stayed, I get a different sample mean, right? So this is estimating the variance of those sample means, right? Craig, what's your sample mean?
My sample mean
Yeah,
on the road,
yeah.
I've got 34.732.
So a little different than mine, right?
Yeah.
And what are your number of employees who stayed? 84?
Yes.
Okay. And what's your variance?
28.39.
23.89?
28.391.
Oh, wow, you got a big variance, bigger variance than I got.
Yeah.
Right? What's your standard? This right here is not standard error yet, right? What's your variance of sample means? What's this number?
Mine is 0.338.
Okay, pretty close to what I got, right? Quimar, what's your mean percent on the road?
Mine's 34.575.
Okay, so we're all pretty close, right?
Yes.
We have 3 samples, they're not equal, right? We don't expect that, right? So because the sample means vary amongst us, this right here is an estimate of that variance. You understand? This is an estimate of that variance. When I take the square root of this ratio, I take a square root of that ratio. Whoops. When I take a square root of that ratio, I get an estimate of the standard deviation in these sample means. And I mean mean, I'm saying means plural, right? Weimar, what is the estimated standard deviation of your sample means?
I got 0.495.
0.495. So pretty close to mine. What is yours, Craig?
0.581.
So pretty close to mine, right? Those are all estimates of the standard deviation of these sample means, right? This is also known as a standard error. It's also called, it can be called the standard deviation of the sample means, or it can be called the standard error of the mean, right? And then we all understand the alpha divided by 2, right? The alpha divided by 2, we have to, yeah, it hasn't changed, right? It hasn't changed. Now, because we don't know the true variance, right? If the true variance was 25, right? If the true variance was 25, we all have the same standard error of the mean. Everybody type 25, the variance percent on the road. We all have the same standard error now. Craig, you change this to 25. You have the same standard error of the mean as I have.
Hold on. Variance percent on the road.
Change it to 25.
Okay, and now it's the same.
Yeah. What about you, Quimar? If you change this to 25, what do you have for standard error?
I have the same.
Yeah. See that? If we know the variance is 25, right? We don't use the t-distribution. We don't have to worry about the degrees of freedom, right? But that's not the case here, is it? We don't know the population variance. So do a control Z, right? Do a control Z to go back to the sample variant, right? Go back to sample variant. Okay. So we all have different standard errors of mean because we don't know the population variance. We're using an estimate population variance, right? This is why we have to use a t-distribution. The t-distribution requires degrees of freedom, right? Degrees of freedom are the sample size minus what? 1, right? My degrees of freedom are 83. We have to use the t-distribution. T-distribution looks a lot like normal distribution, right? Here's the t-distribution. Yep. So, whoop. Here's the normal distribution. Oh man, it messed it up. I guess I can't do that. So here's the t-distribution, right? The inside area is 95%. The area in the tails is your alpha, 0.05, right? And then you divide that alpha by 2 and you get the area to the left of your critical value, right? So this is our critical value when there's only 10 degrees of freedom. As I increase the degrees of freedom, well, degrees of freedom equal to, I don't know, 40, right? The distribution shape changes. It becomes closer and closer and closer to the normal distribution, right? It's getting closer. If we go to 80, if we go to 83 degrees of freedom, right? Oh, it should be 05. 0.025, right? 0.025. And so let me start over here. We got a lower tail probably of 0.025. We'll start out degrees of freedom of 9, right? Our t value is negative 2.263. As I increase the degrees of freedom, right? My t value is getting closer to 1.96, right? Getting closer to 1.96. Yeah, so at 59 degrees of freedom, I'm pretty close to 1.96, right? What about 83? At 83, I'm pretty close to 1.96, right? If I go to 839, I'm at 1.96, right? So degrees of freedom of 83 produces a t value of negative 1.989. We can get the same thing in Excel if we click on this and we add that area under the curve to the left of negative 1.989, and then we do comma, we click on the degrees of freedom. We're going to get something really close to 1.96 that was up here, right? So our critical value is 1.989. Oh, our standard error, my standard error was 0.531. Alpha divided by 2 is 0.025. My degrees of freedom are 83. The margin of error is it pretty small? Let's calculate it, right? So I got critical value times standard error, right? See that? I got the critical value times the standard error. That is the margin of error, right? But my margin of error here is pretty small. Okay. Lower limit of my confidence interval is my sample mean minus my margin of error. In my worst case scenario, or I should say the best case scenario, a smaller number is better, right? For the company. Well, maybe not necessarily here, because maybe you know the company needs its employees on the road, right? If the employees are on the road, they're going to lose customers, right? So my I guess worst case scenario for the company, best case scenario for the employee, minus 33.351. The upper limit is a sample mean plus margin of error. My margin of my confidence interval is very tiny here. It's not very big. Did you guys get it all? Then I'll go ahead and center this. Hang on one second. All right, you guys have any trouble with that problem?
Nope.
Okay.
No.
Now, let me ask you this question. This is a 95% confidence interval, right? Can I say, is this a true statement? The probability of the true population mean being in that interval is 95%. Can I say that?
One more time.
I want to know if this statement is true or false. The probability of the true population mean, which we can never know, that probability of it being in between those two numbers there, is that probability 95%?
Yes.
Now, most people will say yes. Even the editors of a journal of psychology would say yes to that, right? But that is actually false. The probability of the true population mean being inside those numbers, it's either 1 or 0. It's either in there or it's not. If it's in there, the probability is 1. If it's not in there, it's 0. You don't know. You don't have a clue. Bill Gates could have skewed this sample, right? LeBron James could have skewed the sample. You don't know, right? You don't know if you don't know if the population means in there or not, right? What you can say is that if I repeat this experiment 100 times, right? How many times have we replicated it tonight? We've replicated it 3 times, right? Do we all have different confidence intervals? Quaimar, is your confidence interval different than mine?
Yes. My conference interval is 33.59. Oh no, yeah, 33.591. It's my conference interval.
Okay, that's the lower limit, right?
Yes.
And the upper limit is about 35?
My upper limit's 35.559. So it's really
Okay, and then
close.
Craig, same thing with you, right?
It is 33.576 and 35.888 respectively.
Okay, so we have 3 different confidence intervals, right? We've replicated this experiment 3 times. Imagine if there are 1,000 people on the Zoom call. We would have 1,000 different confidence intervals, right? What we can say with regard to 95% is if we have 1,000 people on the Zoom call and 1,000 people had different confidence intervals, what we could say is that we expect 950 of those 1,000 confidence intervals will contain truth. 950 of them will contain truth, the true value. We can say we expect 50 of them to not contain the true value, right? That's what we can say. Now, if there were 10 people on this call, right? No, say if there's 100 people on this call, then we could say 95 of those confidence intervals will contain 90. We expect 95 of the 100 to contain the true value, right? We can expect 95 out of 100 to contain the true value, right? If we have 10 people on this call, right? If there are 10 confidence intervals, and you can expect how many contain the true value. You can expect 9.5 contain population mean, right? Now, because there's only 3 people on this call, right? We only have 3 samples, right? So if we only have 3 samples, therefore we only have 3 confidence intervals, how many of those 3 should contain the population mean, the value that we cannot know? 2.85, right? Now, suppose I was on this call by myself, right? Or in reality, maybe we only do this once, right? We only do it once. We don't do it 1,000 times. We don't do it 100 times. We don't do it 3 times. We only do it once, right? If we only do this once, how many of the 1 do we expect to contain the truth? Well, rounded, it's 1, right? We expect that 1 interval to contain the truth, right? The probability that it's in there is 1 or 0, right? If it's in there, the probability is 1. If it's not in there, it's 0, right? We don't know, right? We're confident. We're confident that it's in there, right? That's not the same as the probability that it's in there is 95%. Those are 2 different statements, right? 2 different statements. Pretty confident that population mean is in between these 2 numbers. We're pretty confident, right? It could be the case that it's not in there, right? It could be the case that it's in there. It could be the case it's below the lower limit. It could be the case it's above the upper limit. We don't know, right? So we have a pretty good idea of where it might live, right? But again, a sample can not be representative if a Bill Gates or LeBron James ends up on our sample, right? All of a sudden, it's not really representative of the population, right? Or maybe a person who made a mistake in the sample maybe entered numbers in wrong, and we just happen to get a person who entered the numbers in wrong, right? Okay. Now the 95%, if we replicate this for what? Time spent on the road for those who quit, right? What do you notice about the confidence interval for those who quit? What do you notice about the confidence interval for those who quit? Both numbers are bigger, right?
Yes.
Yeah.
So why are people quitting? Because the ones that quit do what? At best, spend 48.73% of the time on the road. At worst, spend 51.39% on the road. How about those who do not quit? For those who do not quit, at worst, they spend 35.463% of the time on the road. At best, they spend 33.351% on the road, right? So we're keeping the employees that tend to do what? That are home more often, right? We're keeping employees that are home more often, right? And then here is a confidence interval for the difference. So if I were to take this, right, this minus the mean, what's the mean for those who quit? We can calculate it. If I just average these two and divide by 2, so the sample mean for those who quit is 50.6, right? The sample mean for those who stayed is 34.407, right? If I take the difference of these two, take this difference, I get the center of this confidence interval, right?
What was that what was that other number you used to get the 15.653?
Yeah. Okay, so this right here, what I did is I averaged these two, right? I averaged those two to get 50.6. Why? Because this number is smack dab in the middle. Why is that? Because we're subtracting 1.056 from it. We're adding 1.056 to it. Right? If I add these two numbers up, I divide by 2, I'll get the mean, right? The mean is right smack dab in the middle, right? So the mean of this, the number in the middle of these two numbers is 50.6, right? You see that? I add these two numbers and divide by 2 to get the mean percent on the road for those who quit. Right? Then if I subtract these two, I get the mean difference. Get the difference in the means. Let's call it difference in the means, right? If I take this difference, right? If I take this difference, I get 15.65. If I average these two, right? If I average those two, I get 15.65, right? So this right here is the 95% confidence interval for the difference in the means of those who quit and those who stayed. And it's 13.96 and 17.84. What is this? What does this confidence interval mean? Right? It says at best, right? At best, the difference in the percent on the road, the difference for the percent on the road is 13.96, right? So the people who quit, right? Their percent on the road is almost 14 percentage points higher than the percent of people on the road who do not quit, right? And this does not contain 0. This interval does not contain 0, right? And because this interval does not contain 0, what can we say? Because 0 is less than the confidence interval, we are 95% confident employees who quit logged more time on the road than employees who did not quit, right?
And therefore, that will increase the likelihood that employees will quit the firm.
The more, so what we're saying is, yeah. So what we're saying here is the more you require your employees to be on the road, the more likely those employers are going to quit, right? So spending too much time on the road increases the likelihood that employees will quit your firm. Spending too much time on the road is not the only reason why employees quit your firm, right? It's not the only reason, right? There are other reasons, right? Maybe there's discrimination. Or maybe white people aren't on the road as much as black people or brown people or Asian people, right? Because maybe the owner is white, right? There are other reasons why people are quitting your firm, right? But this is just one of many, probably, right? You need multiple regression analysis to figure out what factors are driving your high turnover rate, right? And high turnover can be bad for business, right? Like when you go to McDonald's and you got a seasoned employee in there, he's got his headphones on, he's taking orders at the cash register, he's taking pickles off, right? He's adding caramel, or he's adding Oreos to a vanilla milkshake. Meanwhile, he's taking an order in the drive-up lane at the same time. Guy's awesome, right? Then you got the other guy who's new, who can't figure out how to take the pickle off the Big Mac, right?
If you don't know how to take a pickle off, you are in serious trouble.
Well, I mean, within the computer, right? When you're making a customer order. I've seen people who are on the cash register. They're like, I don't know how to take the pickle off the physically it's pretty easy not to put a pickle on a burger, right? But on the software where you're ringing up the order and the customer wants a custom order, I've seen employees struggle to find how to take that pickle off, right? And if you don't pay your employees, that are really good, you're going to lose them, right? Or if you don't give them kudos, right? Or if you don't maybe recognize how good they are, like, if you're the employee of the month, you get, I don't know, Broadway tickets, or you get tickets to the football game, right? Or you get a parking space. If you don't recognize really good employees with either higher pay or benefits, right, that make them feel good about themselves, they'll leave, right? And so you'll be left with employees who can't take a pickle off the Big Mac when the customer requests it, right? So it's really important that you understand turnover and what drives turnover. And this is just one aspect of what can drive turnover, right? Now, we didn't do the work on this, right? If you're interested, you can repeat this work here to get this number. These numbers require a standard error that is like a weighted average of this standard error and the one that goes along with this one. So this one's a little bit more difficult to get to, right? But I spared you the details on these two confidence intervals because you basically just need to understand how a confidence interval is built in order to use it to make better business decisions, right? Any questions?
Nothing.
Okay, so I need to press enter here, right? By pressing enter, we got 100%. All right. Same time next week.
Yes,
Yes.
sir.
All right, you guys have a good week. If you need
You
help
too.
with anything,
You
make sure
too.
you email me, right?
Yes, sir.
All right, have a good
Okay.
night.
Bye.
You too.